We will start today doing problems on chapter 4. Okay. In this chapter, we will apply the Reynolds transport theorem for different cases, for mass, for momentum, and for energy. Okay. The first application of this Reynolds transport theorem is to set B equal to 1. And when you set B equal to 1, if you replace in the Reynolds transport theorem, you get the continuity equation. Okay. So, and the second application is to replace V in the Reynolds transport theorem. Then you will obtain the force balance equation. And at the end, if you replace by energy, you will get the second law of thermodynamics. So let us start with the first application of Reynolds transport theorem, which is the continuity equation. In the following problem, water flows steadily through the round pipe shown in the figure. The entrance velocity is uniform equal to V0, while the exit velocity is given by U equals to U max, which is a certain constant, times 1 minus R over the radius to the power 1 over 7. Determine the ratio U0 over U max for this incompressible flow. Okay. So here you have the velocity profile at the exit, and you have that the velocity is uniform at inlet. So if you want to present what we have here, we have here U0, okay? And at the exit, we have the profile, the varying profile U. So if you want to find a relation between the maximum value of velocity at the exit U max and U0, because we want to relate velocities, we should think about applying the continuity equation between the inlet and the outlet. So we will say that here, first it's an incompressible, okay, incompressible flow, so rho is constant, okay, and as you can see, it's a steady application. So steady, because the profile of velocity is independent of time. Steady application. Okay, so I can say here that by applying continuity, I have that m dot in equals to m dot out, and because it's incompressible, I can say that q dot in equals to q dot out because of the incompressible flow. Okay. Now, concerning the Q1 is very simple to find. Why? Because we have a uniform velocity profile at the inlet. So for Qn, it's very simple. Q dot n is equal to the area A1 times V1, and V1 is equal to U0. Okay, and A1 is simply the circular cross-sectional area, which is pi r squared. So it's equal to pi times r squared times U0.
Doctor, here Q dot n equal A1 times U.
A1 times U0. U0 is, or V0, they call it V0 here. So V0. Okay, which is the velocity at inlet, the inlet velocity. Okay, because I told you that the entrance velocity is constant equal to V0, and it's known. Now we want to, if you want, they mixed names. They put here V0, then they use U0. So it is the same. U0 and V0 in the problem is the same. Okay. Now, the second step is to find the flow rate at the exit, Q dot out. Okay. Why it is little bit challenging to find the Q dot out? Because you have a variable velocity profile. And when you have a variable velocity profile and you want to find the volumetric flow rate, then think about integration. Okay? So, and to know how to perform the integration, you should try to select elementary area where the velocity is not varying. To understand this, let us take a cross-sectional area of the tube. If I take a cross-section, Okay, the velocity is varying in the radial direction. So here it is maximum at the center, and it is decreasing until reaching 0 at the wall. Okay, so now I can say that uh, an elementary area of same velocity will be of which form?
You mean steady or unsteady?
No, I mean I want to select an area where the velocity is the same. So look, if for example, if I take a certain circle of radius, if I take a circle of radius r, all points of this circle, all points will have the same velocity. Why? Because velocity is varying with radius. Okay, as you can see in the expression, u equal to u max times 1 minus r over r to the power 1 over 7. So here at the center, you replace r by 0. What do you get? You get u maximum. As you go far from the center, your velocity decreases until at r equal big R, which is the radius of the tube. If you replace, you get 1 minus r over r, which is 0. So at the wall level, the velocity is 0. Okay? So you can say here that the velocity is constant for the same radius. This is why the idea here is to consider an elementary area. You take a thin disk. Okay? If you take a thin disk, you can say that over the thin disk, the velocity is not changing. So if I take, this is my elementary, let us draw it in another way. This is the elementary element I should take. Why? Because for this element, the velocity is not changing. Okay, so I will take a very small disk of here of thickness. The thickness here is dr. Okay, and I can say that for this area I have the same velocity. Why I am doing this? Because I want to find the total flow rate, and I can write that the elementary flow rate dq, okay, dq dot of course, is equal to elementary area dA times velocity at this area. Okay, so here your elementary area will be the thin disk here. So what is the expression of dA? dA is equal to 2 pi r dr. Okay, then for this small element, okay, I have the same velocity, and I can replace the velocity by its expression, which is u max times 1 minus r over r to the power 1 over 7. So I can now find the expression of a small elementary volumetric flow rate, and then to find the total flow rate, all I have to do is to integrate. Okay, so let me repeat this. I want to find the total flow rate. The elementary flow rate is, I can write here that the elementary flow rate dq is equal to a velocity at a certain radius r, so u at a certain radius r, times the elementary area for which I have the same velocity, which is 2 times 2 pi r dr. Okay, so now I will integrate here, I will integrate this term between which boundaries? From what to what I will integrate? Look, your radius is varying, r is varying from 0 to big R, as you can see here in the figure. So if you want to cover the whole circular area, you should integrate from 0 to big R. So I should integrate this function between 0 and big R. Okay, now all I have to do now is to replace the u by its value. Okay,
Okay.
so I can say that q total is integration of dq. Okay, so q dot total is equal to integral of dq between 0 and r, of course, between 0 and r. And now, to be able to integrate, I will replace u by its function of r. So it's equal to, ur is equal to u max times 1 minus small r over big R to the power 1/7.
طب دكتور هي يو تايمز دي اي صح؟
مظبوط، هي يو تايمز
واليو هي يو ماكس.
لا، اليو هي يو طلع بالاكسبريشن يو هي
يو
مش
ماكس
بس
هي
يو.
الجيفن يو ماكس 1 minus r
مظبوط
over r.
مظبوط. Okay, so I am replacing now u by its value. Then I should multiply by 2 pi r dr. Okay, so until now I just replaced ur by its value, and I want to multiply this value by 2 pi r by
Doctor,
2 pi r dr.
question in the chat.
Yalla, one sec. Yes, why 2 pi r and not pi r square? Because if you do pi r square, you obtain the total cross-sectional area. So look, I will do a figure here to explain why. If you consider here the whole, if you do pi r square, you are considering this whole area, this one. Okay? But as you know, this area, for this area, you don't have the same velocity everywhere. Okay? So when you do ur, you should multiply by the area for which you have this velocity. So the area for which you have ur is at a certain radius r from the center. So now this is, if I take this is r, okay, this is a certain distance r from the center. The elementary area that I can take from the center will be a very thin disk centered at my origin. So here, if you want, if I take a small thickness, for this element, I can consider that all the elements here, all the elements are equidistant from the center. Okay, and for this elementary area, neglecting the thickness effect, I can say that for this elementary area, all points are at one distance from the center. So all points will share the same velocity. All these points will share the same velocity, which is ur. Okay, and as you go far from the center, your velocity will decrease, it will vary. So since you are integrating, you will consider an elementary area for which the velocity is equal to this expression. And this elementary area is a very thin disk centered at O, at the center. Okay? Now, if you want to calculate this elementary area, dA, what should you do? dA, it's the perimeter times the thickness. It's equal to the perimeter times the thickness. Okay? Which will give you, what is the perimeter here? It's equal to 2 pi r. Okay? And the thickness of this element is dr. Okay? This is why your elementary area is 2 pi r dr. And why we selected this elementary area? Because at any point of this area, I will have the same velocity ur. Okay? Is this clear now? Okay. So let us continue. Now, this is your equation, okay? You end up with the following equation. The first term is very simple. For the first term, no need for integration. They did integration, but you will obtain the same result as we did, which is u0 times the total area. Here you can directly multiply by the total area, which is pi r square. Why? Because the velocity is uniform over the area. While for the exit, you cannot do this. You cannot, if you want to multiply by pi r square, which velocity you will choose? You have a velocity that is varying from the center towards the end. This is why you should do integration, okay? And your integration is from the center to big R, which is u function of r times 2 pi r dr, okay? So now all you have to do now is to perform simple calculation. You integrate for the boundaries
Doctor?
given. Yes.
The profile at the end, the velocity profile at the end, is the same for all the pipe, or هنا just for that little part?
Once it is fully developed, it will be the same everywhere. But you need a certain, you have a certain region where it is changing. The profile is, we say that the profile is developing. At the end, it will become fully developed, and we will learn how to determine these profiles in next chapters. But now, you are just interested in the exit profile. You don't care what is happening in between, because you are applying your continuity equation between here and here. So whatever is happening in between, you don't care for. Okay?
Okay, perfect.
Okay. So now, once you perform your integration, then you can easily find a relation between U0 and Umax. And it's expected that Umax will be higher or lower than U0. What do you think? Umax should be higher or lower than U0? Who can tell me?
Higher?
Very good. Why it's higher? Because if you want here, U0 is like an average velocity, okay? Because it's the same everywhere. However, here you have zones where you have zero velocity. This is why to compensate for this and obtain the same flow rate, you should have at the center a much higher velocity. So Umax here, you have much higher velocity than U0, and it's decreasing until zero at the end. So as you can see here, you can see that the ratio of U0 over Umax is smaller than 1, which is expected. Okay? Any other question for this problem?
دكتور هلا
دك-
يمكن
Yes.
هلا الكويستشن يمكن بحد ذاتها انه اتس ايزي، بس هي ذا واي اوف ثينكينج انه احنا كيف بدنا نفكر، كيف بدنا نبلش.
Okay.
ايه
أول
دكتور،
شيء
انا
want
شيء
to...
كمان اللي ما فهمته انه هيدي السيمي سيركل
إيه.
اللي عملناها، انه انا كيف بدي افكر فيها هاي؟
Okay. أول شيء لأنه you want a relation between velocities, okay, you should think about continuity equation. لأنه the velocity profile is related to continuity, because the continuity will tell you that you have conservation of mass flow rate, and the mass flow rate is directly related to velocity profile. Okay, so whenever you want to get relation between velocities, try to think about the continuity first. Then why I choose this area? I will repeat for you, because I told you if you want to write Q equals to A times V, when you just write this means what? This means that you assume that the velocity is the same for the whole area, yes or not? When you write Q equal AV, you shouldn't have the same velocity everywhere in the area. If I have variable velocities, if I have variable velocities on my area, can I just say, if I want to apply Q equals A times V, which velocity to choose? I don't know, because I have variable velocities along the radius here. So I cannot use anymore this formula, because the velocity is not the same everywhere. So what do I do? I think about integration. I think about taking a small element where the velocities are the same everywhere in this element. And since your velocity here is varying with what your velocity? Your velocity is varying with r, which is the distance from the center. So you can say, if I take a circle, for example, this circular line, at any point of this circular line, I will have the same velocity. Why? Because all points are at one distance from the center. Okay? Now, since for a circular line, I have everywhere the same velocity, and since I want to take an elementary area, then I think, what about taking a very small thickness? Because if I take a very small thickness, okay, I can consider that I have negligible variation of velocity. So when I take this very small thickness, I can say that over this area, over this area, I will nearly obtain the same velocity everywhere because the thickness is negligible. Okay, so you should think about which area will give me nearly the same velocity everywhere. The area that will give me the same velocity everywhere is 2 pi r dr. If you choose any other area, your velocity will be varying along this area. So when you take this elementary area, you say that for any point in dA, so now for any point in dA, okay, I have the same velocity. And what is this velocity? What is this velocity anywhere here? It will correspond to the velocity at radius r, which is for this dA, okay? dA is at distance small r from the center, okay? So for this elementary area, what is my velocity? It is ur. So I have the same velocity ur everywhere for this area. So same velocity ur, okay? Now, I can say that the elementary flow rate, okay? So the elementary flow rate dq, okay, I can write that dq is equal to the elementary area dA times ur, okay? And I express dA function of r to be able to integrate with respect to r. So it's equal to 2 pi r dr, okay? And now, since you obtained the expression of the elementary flow rate, in order to find the total flow rate, all you have to do is to perform the integration. So always, when you have variable velocity profile, think about integration. Okay? I hope it's clearer now. Any other question because before I start a new problem? Okay, another problem. Water enters the bottom of the cone in the figure at a uniformly increasing average velocity v equal k times t. D is very small. Derive an analytical formula for the water surface rise ht, assuming that at t equals 0, h equals to 0. So first, since you have velocity, the inlet velocity function of time, so it's an unsteady application, okay? So here v is equal to kt, so I have my equation will be unsteady. So I should take into consideration the variation with time, okay? So I go to my course and I say, what is the formula for transient continuity equation, okay? The formula is d by dt of integral rho dv minus m dot n, and in general you should add also plus m dot out, but here you don't have any mass flow rate out. This is why they didn't include it. So in general you should say also plus m dot out.
هذه دايما بس يكون عندنا كون نستعمل هاي الفورمولا.
No, ما خص الكون. Whatever is your shape, okay? If you have a velocity, your inlet velocity is varying with time, okay? So what is happening here, you are filling your cone. Because you are filling your shape, then the level of water is increasing inside. So you have a storage term, okay? Whenever you have a storage term, this means you don't have a steady application. Why? Because if you take a picture of your cone at several times, you will see that the level of water is increasing. So it's not a steady application. To have a steady application, you should have the level of water constant at any time. Okay? So for any problem of unsteady, where you have an unsteady application, you should apply the following rule, because the mass of water inside is varying. So you will say that derivative with respect to time of integral rho dv, this term represents what? It represents the variation with time of the mass of water inside my cone. Okay? So this term represents variation of water mass inside the cone. Okay, this is This is the first term.
دكتور ليش هون ام دوت اوت زيرو لانه ما في water going out.
Yes, exactly. ما في outlet. So this is your, if you want, if you expand little bit, this is your cone. You don't have any outlet. هلا اكيد اذا بتضل تعبيها لحديت ما ينتلي الكون بصير يوقعوا لبرا الووتر. But here we consider that we have a very large, يعني a very high height, and we are filling the cone. They didn't give us any information that the water will be to the upper limit and then will begin to fall out. Okay, so we consider here that we are just putting water in order to raise the level of water in the cone. And of course, when we reach the value needed, we will stop. We will not have water out. Okay, this is why in this application m dot out is 0. Okay, now if I want to evaluate my terms, first for m dot n, it's very simple. Why? Because we have the inlet velocity, okay, and we have the diameter here. So we can say that m dot n, so m dot n is simply equal to rho times the velocity v times the area of the inlet, okay, which is equal to rho, the velocity is k times t, so it's kt, times the inlet area, which is pi d square over 4, okay, over 4. So this is the expression of m dot n. Okay, now I still need to see what is this term in d by dt integral rho dv. Okay, first let us evaluate integral rho dv. Rho is what here? Is the density of water. The density of water is a constant, okay, so we can take it outside of the integration. So what do we have? So when we have integral rho dv, integral of rho dv, of course over the control volume of the cone, is equal to rho times integral of dv. Integral of dv will give us what? When we integrate dv, this means we are integrating dv over the volume, So what do we get? We get the total volume, okay? So when we do integral dv, we get the total volume. So it's equal to rho times v water inside, v water total inside the cone, okay? Inside the cone, okay? Now, we can replace integral rho dv by rho times v. But what is the volume inside the cone? How to calculate the volume inside the cone? Who will tell me? Look, you have a conical shape, okay? And they give you this information, d is very small. Why they told you d is very small? So that you consider here that you can really nearly treat it as a cone, okay? You can neglect the effect of the small hole here. You can consider that you have a cone. So your volume is a conical volume of height h, okay? The height is ht, and if you want your base is of radius r equal to what? By geometrical analysis of the figure, you have that the radius of the cone at the base of the cone is equal to h times the height of water in the cone times tangent of angle theta. Okay, so now I can replace in my equation.
دكتور بس ليش h tangent theta كيف جبناها؟
Okay, because look in this triangle, you consider that this is h. H is this length here. It's the water level inside the cone. And R is Do you hear me now?